All right, let's get started today. All right, welcome. So this is lecture 8 for our CS176P class. Today we are going to talk about software-defined wide area networks. And before we talk about wide area networks, let's try to do a quick recap of what we learned at the last lecture. In last lecture, we talked about software-defined internet routing, and we discussed that how uh, internet exchange points were the right place where such a change can be enabled in an incrementally deployable manner. And we talked about the fact that building a flexible and scalable SDX is non-trivial, right? And we talked about how like the research papers like SDX and ISDX address these challenges. It talks about a new abstraction which simplifies how these participants at the exchange point can express their flexible control programs. So the abstraction is called virtual SDX switch abstraction. Here, each participant gets a virtual switch to express their own programs. So, like they don't have to worry about what others are writing. And then under the hood, SDX is responsible for composing, which is a piratic term, composing the policies or programs expressed for each of these virtual switches, right? And then we also talked about the scalability challenge, which came from the fact that, or which arises from the fact that, you know, even though we enable a lot of flexibility at the exchange point, everybody else outside the exchange point is still using BGP, right? So we want to make sure that these exchange points are in compliance with the BGP routing protocol. And to enable that, SDX had to, like augment the programs that are expressed by these participants that results in a scalability challenge. And to address that scalability challenge, SDX and ISDX both had different types of approaches. But the common theme between the two was that they were trying to offload the complexity to the packet's metadata, right? So from the switch, they were offloading the complexity to the packet. And SDX approach was that it was leveraging this concept of forwarding equivalence for the prefixes at the exchange point. And ISDX was, like using a completely different approach where rather than focusing on prefixes, it was focusing on the participant. And, among the two, ISDX has a really good performance in terms of scale, but SDX was the first type of work in this research direction. Okay. So I think in today's class, the goal will be that we will be learning about wide area networks in general. What are wide area networks? We'll learn about how Google transformed its wide area network, and what type of wide area networks are there, and which type of wide area network we're going to focus on. We'll try to understand that. We will also be learning about the design choices that Google made while building it, and I will try to present it from the perspective that what are the design choices which are a bit more generic, right? So not specifically zooming too much on Google's choices, but in general, anybody who's building such a software-defined wide area network, what type of choices they have to make. And then we'll dig a bit deeper into the implementation details as well. But one thing which is important and unique in this lecture compared to like what you read in the paper was there is a similarity between ISDX that we learned, as well as the system that we're going to learn here from bForce perspective, right? So we'll also try to understand how those two systems are similar to each other, or in some sense, how are they exactly different from each other, right? So we'll try to understand those nuances as well. All right, so let's begin. Now, when you're trying to access a content, say Google, how does it really work? From your laptop, you send a request, it goes over the internet, and then Google responds to it. So it seems like Google is one entity sitting somewhere at the corner of the internet, but that's not really the case. In practice, Google is widely deployed, and there is a Google front end which is closer to you. When you make a request to a Google content, then using the DNS protocol, which is like, it will, when you send a DNS request, you will say, okay, www.google.com. So this will be going through Google's DNS server, right? This request, and then Google's DNS server is supposed to respond with an IP address about which IP address this request should be directed to, right? So that gives control to Google. Like, and I'm just calling Google, but this is how most of the services work as well. That this gives them control to dictate which IP addresses the client should be connected to, or their request should be sent to. So it gets redirected to a front end, which Google knows is closer to you, right? Because there are so many protocols that most of these entities use to figure out what is the right front end for you, right? Typically, your IP address like reveals a bit about your location, so that gives a sense of, okay, what is the right front end to which this request should be directed to. Now you get connected to the front end, and the front end is basically serving content to you. And most of the cases, front end will have a lot of static content already cached, right? So the Google icon that you see, that's something which is available at the front end itself, and it's coming in directly. But then there are so many other dynamic aspects of the content that you're looking into, like information about your account, the emails, and all those things. Not everything can be cached at this front end. So there are backends as well, right? So these backends are sitting somewhere else as part of Google's network. And then the content which is not available at front end will request it from the backend, right? Now, these backends are not just at one location; they are geographically distributed. The geographical distribution can be if it is US, then the distribution is the penetration is more dense. So you will see all big metro areas having some data center for these cloud providers. But give me one sec. Making sure that the sharing is still on. Give me one sec. All right. Okay. So I was saying that these backend servers are basically the data centers, and if it's US, then you have a much dense deployment. All the big metro areas, like think of New York, Chicago, LA, they will have data centers. Like these data centers are deployed based on the population, so that the delays between the front ends and the back ends are as less as possible. So like there is a natural gravitation towards the areas which are a bit of a population hub, right? So now there are two types of wide area networks that exist for these entities. So one is that connects the front ends with the back ends, right? So if you go back to this figure, like this front end needs to talk to the back end, right? So those back ends can be, something which is very close to you geographically, but then technically this front end should be capable of talking to almost all the backends of this content provider, right? In this case, Google. So that's one type of wide area network. And in Google's case, it's called B2, right? So I don't know what is the naming convention where they came up with this name, but it's called B2 for Google. Then there is a wide area network that just connects the backends with each other, right? So, like all these backends that we have that are connected with each other, that is the type 2, or it's called B4, and that provides this inter-data center connectivity. So now you might be wondering why these data centers need to talk to each other. Think about these servers are running distributed state, right? So they are think about the social media, social feed that you see. So, like what you see is something which might be affected by the actions taken by somebody else whose state might be maintained at some other data center, right? So then like all these data centers, all these servers have to synchronize with each other, share that data with each other so that there is eventual consistency on the page views and all the things that you see on your dynamic service, right? Think of Gmail or Google Plus. I don't know if Google Plus is still out there, but that was kind of like a social media equivalent for Google, right? So this is the data center communication or inter-data center communication. It has like initially the type of services, the dynamic services that were offered were relatively low. So, there was not much of traffic between these data centers. But now, as the footprint of the users geographically distributed has increased, as well as the complexity of the applications, so there has been a huge increase in the amount of data that is being exchanged between these data centers, right? The result that you're looking at, the graph that you're looking at is relatively old, but still captures the essence that there hasn't been an exponential growth in the traffic volume. And in fact, like from what I've heard, or like some of the latest presentations that I've seen from Google, they say that their B4 wide area network, the traffic carried by B4 has exceeded B2, right? So there is a lot more traffic going on between the data centers compared to what is being interacted with the end users. So now that we understand that, okay, there are these wide area networks, they need to talk to each other, let's think about how, or let's learn how conventionally these connectivity, inter-data center connectivity is provided, right? The conventional approach is called MPLS. So MPLS is something which is very traditional tool, which is, I would say, like a good version that came out of the non-SDN era. And MPLS has been adapted in different ways in the SDN era as well. But the key idea with the MPLS is that it views the network, or it kind of like virtualizes the network in terms of tunnels, right? So you have ingress and egress tunnels. So rather than thinking about what is the routing path and all those things, basically multiple possible routing paths between ingress and egress are viewed as tunnels, right? And then at egress, at ingress, the ingress server is going to decide. It typically uses ECMP to split the traffic between tunnels with the same egress, right? And it does support some traffic differentiation. So you can set priority levels for different type of tunnels. And then the packet itself can carry the DSCP bits, which will help the individual routers at the hops discriminate between packets depending on the DSCP bit, right? So this is what MPLS is, and like this is how MPLS was or is used. Like MPLS is still used by a lot of networks that have not really adapted software-defined networking. So this is how it works. There are a couple of problems with it. One problem is about efficiency, or I would say the biggest problem is about efficiency. Why efficiency matters is that there has been, as we saw, that there has been an exponential growth in the volume of traffic that these networks have to carry, right? And if these networks are not efficient, which is that they're wasting resources most of the time, then the companies have to invest in the same order as the traffic volume is increasing, right? And given that this increase is exponential, the cost, the infrastructure cost that the companies have to invest to scale up the volume of network, the volume of traffic that is being carried over these networks is prohibitively expensive, right? So there is this need that these underlying networks, the wide area networks, have to be very efficient, right? So conventionally, when MPLS was used, these networks were designed such that they are typically operating at around 30%, 50% of the peak demand, right? So sometimes there's a peak in the network, and these networks or these networks should be capable of handling those peaks. So they are kind of over provisioned such that they can support twice the increase in traffic volume. Like this figure that you see is a very good example of that, right? So on the axis here, we have time. I'm trying to recall, I think think of it as a day, right? So think of it as a day, and the data points on the x-axis being the hours. So what happens here is that the mean traffic is around, say, this is normalized, so it's around 0.5, 0.4, right? Between 0.4 and 0.5. But then there are instances when the peak actually goes to 1, right? And because this is normalized, so 1, we don't know what is the scale of 1, but it goes to 1, and that's what it is normalized with. What is important is that the peak to mean ratio is 2.17, right? Let's think about it twice. So basically, mean means that most majority of time you are around this level of 0.4, 0.5, but because for some instances your traffic has to support the peak demand, so it has to be provisioned for that type of demand, right? And that happens because there is lack of coordination between different services, right? So what do I mean by that? Let's try to unpack that with the next slide. So in this slide, for the same traffic, what we have done is that we have separated the traffic based on whether this is a background traffic or this is a non-background traffic, right? So when you think of background traffic, you can think of things that are not time critical, right? So or they're tolerant to some type of delays, right? So they're not critical traffic. It's just synchronization of information. They're fine if they are done at the scale of a day or something, right? So background traffic, if you split between the two, you see that, like the non-background traffic, its peak demand is around like 0.4 or something. And then it's the background traffic that is making all the difference. So instead of letting the background traffic, run the demand to the roof, what if we rate limit it, right? We rate limit it such that, we can, like, if there is, non-background traffic going on, it is eating up all the resources, then you want to deprioritize the background traffic. And like once the non-background traffic has some available resources, then you allocate that to the background, right? So if you do that and put a peak at say 50%, like I won't let, that's my limit, then you can spread this background traffic across the other periods. Whenever there is less demand from the non-background traffic, you can fill that up with the background traffic, and overall you're able to satisfy both the demands. So time critical one, which is the non-background traffic, is working as is, but then the delay tolerant, which is the background one, you're regulating it, adapting the rate for it such that it goes on through the entire period, but it does not exceed, or it reduces the peak demand. So this adaptation or adapting the rate at which you are sending the background traffic is helping you reduce the peak demand for the network, right? And what does this mean? It means that, if I am able to control at what rate these applications should be sending traffic, and also control how exactly that traffic should be going over the network, I am able to work with half the capacity, right? Or in other words, if I've already invested in terms of capacity, I'm like with the same set of devices, I can actually handle double the workload, right? Or double the volume of traffic over time, right? So if the trend is exponential, which means a couple of years down the line, the traffic that I'm going to carry is going to double, then I don't really need to upgrade my infrastructure for that, right? So that is what is critical. And like with MPLS, this is really hard. But this experiment was conducted by Microsoft Research using the data at Microsoft, and they showed that if you regulate the background traffic, you don't really need to provision a network to such exorbitantly high levels. There is another problem with MPLS that the ingress, as I was saying, was making decisions locally about how it is going to distribute the traffic, right? So like in this case, you have three sources, you have three destinations, right? So in some sense, three pairs of ingress and egress, right? So source 2 has two links, and it is the one which is kind of dividing the load into half. So which means that because the path between source 2 and destination 2 and source 1 and destination 1, they have one link that is common, right? So basically they have to share that, right? If they are both using it, then that kind of pulls down the overall demand that S1 and D1 can support, right? So similarly, that goes for S3 and D3 as well. So overall, S2 and D2, because they're doing this local greedy load balancing, then they will load balance the demand across these two links, half and half. And that means that S1, D1 can only use half of that capacity. And similarly, S3 and D3 can only use half of that capacity, right? So this is link level fairness, right? Per link, there is fairness between two set of flows that are out there. So for every link, there is fairness here, right? But overall, it is a bit inefficient, right? A better approach can be that if we send one third traffic for S2, D2 over the two links, right? So this is not fair in a sense that the link that is shared by S1, D1 and S2, D2, right? So S2, D2 is getting a smaller fraction of that link, and S1, D1 is getting more fraction of that link, right? So at the link level, this is not fair, right? But overall, at the network level, it is fair, right? So all of them, all these source destination pairs are actually getting equal share of the resources, and each of them are able to send or satisfy 2/3 of their demands, right? So this is one example in which we can identify or make an argument that because MPLS is only ensuring link level fairness, then that type of greedy resource allocation is inefficient. And if we have a holistic view of the network, where rather than ensuring link level fairness, if we ensure the network level fairness, then we can do a better job, right? So this is also one example of why MPLS is not really a good tool for making good use of the network resources, right? So this motivates development of software-defined wide area networks. And so we are going to talk about B4, which is Google's implementation. But before I dig into that, I want to lay it out that there are more wide area networks beyond Google, right? Especially around 2013 SIGCOMM when B4 was published. In the same conference, SWAN, which is the Microsoft version of software-defined wide area network, was also published, right? So I would say Google started sooner. That's to their credit, but it's not the only implementation of software-defined wide area network, right? So there are common attributes across all these software-defined wide area networks, and like we will talk about them, like those common attributes. So one is that they leverage the service diversity, right? So as we were looking at the example earlier, that there is a diversity in the requirements for different services. Some services that require just synchronization of information, they are tolerant to delays, right? So that is the background traffic that we were looking at in the previous version or the previous set of slides. But then there are some, delay sensitive applications, which are maybe their bandwidth requirement is not much, but they really care about the latency, right? So there is a diversity of different type of applications or services that a wide area network is going to handle. So being agnostic to those applications is not a good idea, right? So all these software-defined WANs are aware of what type of services they're carrying, and then based on that, they can prioritize. Okay, like now I will give more bandwidth to this resource sensitive or the latency sensitive application versus the other one, right? So that's one attribute of all these software-defined WANs. The second is that they enable centralized traffic engineering, right? So the MPLS, as we were looking at, was making some local decisions at the link level that, okay, like, it's going to distribute these, whatever a particular link sees or whatever a particular node sees at the link level, like links at its local level, it's going to enable fairness at that. And then as we saw, like that those can result in inefficient utilization of available resources. And then most of these schemes do dynamically reallocate bandwidth, right? So they don't make these bandwidth allocation decisions at the order of days, right? That will be very slow to react. So because these different type of applications are getting up, getting down, the demands are going up, the demands are going down. So there is a lot of dynamism in the network. So these systems are aware of the demands from different applications from different sites, right, that are trying to communicate, or data centers that are trying to communicate with each other. So they basically have mechanisms in which they are getting an estimate of the projected demand for next 5 minutes, next 10 minutes, half an hour, right? So they basically like get that estimation of demands and then make decisions about how to allocate the bandwidth in a dynamic fashion, right? And another attribute about all these systems is that they enable rate limiting at the edge, right? So what do you mean rate limiting? The good example is the background traffic example that we were looking at earlier, that we are technically rate limiting background traffic to not go beyond a particular rate, and dynamically changing the rate at which it can send the traffic as well. So if there is more latency sensitive traffic coming in, then we want to change the rate at which this background traffic can be sent, and vice versa. Why this is important? Because if we control the rate, then we make sure that these routers are not supposed to hold a lot of packets, right? So if there is less bandwidth available and more packets coming in, then these additional packets have to be buffered at the router, right? If you don't buffer them, then they will drop, and that will basically give a feedback to these TCP sessions that, hey, there was a packet drop, and then their congestion windows are going to drop significantly, right? So typically these routers were, these routers were designed that they had no control over the rate at which the traffic is coming, which means that it can come at any rate, which means that at times you might have to buffer a lot of packets, right? And when you support deep buffers in these routers, then the cost of building those routers or switches goes high, right? So one advantage of this rate limiting is also, like, apart from the efficient usage of the available resources, one advantage is also that you don't require deep buffers in the intermediate switches and routers, right? So that's a huge deal because that helps reduce the cost of these devices significantly, right? So from hundreds of thousands of dollars that these companies were investing in each of these routers, now they can actually build these switches, which are custom made switches, which don't really have a lot of buffers, of the order of $5,000 to $10,000, right? That's a huge change. That's orders of magnitude difference in the cost, which basically gives them a lot of flexibility in terms of scaling over time, right? So with the same amount of budget, they can buy more switches, which means that these switches are designed such that they are making efficient use of the available bandwidth resources. So they're able to they get more mileage out of the same infrastructure budget that they have for handling more traffic in this case. So now let's talk a bit about Google's B4 itself. So Google's B4, which was providing connectivity between different data centers, was a huge visible SDN success, right? So we learned about the intellectual history of SDN, and we talked about OVS, we talked about Nicira, we talked about Onyx. So all these were kind of like initial set of prototypes that were coming out, but then Google basically was one of the first companies that recognized the value of these software-defined networking and how that can actually help them reduce their operational cost. So they started adapting all these new ideas, which was, I would say, was a bit of a risky move. But at the same time, it made a lot of sense for them, right? Because they were tied with these vendors like Cisco's and Junipers, and for them to grow, they had to scale in terms of the amount of data that they can move around, right? But because they were tied to these vendors, that gave them little flexibility in terms of how they can innovate, right? So they for them, networking was a black box, which was technically outsourced to Cisco's and Junipers, right? And that is something which providing that connectivity was one of the key enabler for these companies, and they couldn't really risk to let somebody else handle that. So they had to take control. And that was a natural tussle from business point of view also, which made a lot of sense. And software-defined networking was the right tool at the right time, which enabled these cloud companies. I think like Google, even before the OpenFlow came out, Google was also already exploring what they can do. But since OpenFlow came out, so that kind of catalyzed this deployment effort. So Google kind of started this effort around 2008 or 2010. And the paper that they published before, which was more of an experience paper, was published in 2013, right? So 2013 was, I would say, when this paper came out, was a bit of a pivotal moment for software-defined networking, because this was a huge, validation for all the ideas that were so far considered as academic. But here is the world's one of the biggest company, which is talking about how they've adapted software-defined networking in their own infrastructure. Right? So now, talking about one specific, zooming into one specific site or a data center location, what does that look like? So there is this paper from SIGCOMM 2015, which talks about the type of topologies that the data center network has, evolved to. And the class topology is something which is, very popular. The idea there is that you have this hierarchical set of topologies where all downstream, everybody's connected with the downstream devices, and then then there are these intermediate hierarchies which are connected to the upstream set of routers. So that is theoretically also the optimal in terms of cost, and that has something which has been a natural evolution. There are some other topologies that have been proposed, and especially you probably have heard about Jellyfish in your discussion section. So Jellyfish is another example of a topology that can be technically deployed in these data centers, and it has its own pros and cons. But Clos is something which is widely popular and widely deployed in most of these companies. So there basically there is a set of routers which are providing a set of servers or switches or devices that are providing connectivity to the external world. And then all these connections that you see, right, otherwise are basically providing connectivity to the machines that are within the data center itself, right? So that's the inter-data center communication, intra-data center communication. And then for some of the nodes who want to talk to some data center outside, then we need the inter-data center communication, which will be going via the B4 wide area network, right? So now we will be focusing on this right-hand side corner, right-hand bottom corner, which is the to external, right? So how are these servers getting connected to the external part is what B4 is all about. So the way Google designed B4 was that they thought of it as a transit provider, right? So what do you mean by a transit provider? What is a transit provider? So transit provider is a network that provides connectivity between set of different peers, right? Or its customers. So Tata and what is the other Cogent. These are world's biggest transit provider, and they provide transit services. So basically, if you are their customer, they will advertise your routes to whoever they are either peering with or whoever are their customers, right? So they're basically the provider for most of these networks. You advertise your IP prefixes using Border Gateway Protocol or BGP to these transit providers, and then they will make sure that everybody in the world knows about these prefixes, right? And then like whoever wants to reach to your network will be coming via these transit providers. So similar way, Google basically tried to have a logical separation of this wide area network. They envisioned that or modeled that as a transit provider. So all these sites, you can internally they were basically their own administrative domains, right? So they had their own set of prefixes that were assigned to them. They were using Border Gateway Protocol to advertise their prefixes to the B4 transit, and then B4 was basically using internal gateway protocol to advertise those routes among its router, and then then these routes were then further advertised to other sites, right? So suppose there is a site 1, it has a prefix say 10/8, then it will advertise that to B4 using BGP, right? And then the router which is receiving this update will share this update with other routers that belong to B4, and then those routers will use the eBGP session again to advertise 10/8 to site 2 to site 3, right? So now site 2 and site 3 will know that if they have to send any traffic to IP address that belongs to a prefix 10/8, then they will send that traffic to a router of B4, right? And then B4 will internally figure out, okay, like whatever is the router that is closest to site 1, this traffic should be forwarded to that router, and that router knows that, okay, because this IP address belongs to site 1, then it will forward that traffic to site 1, and the site 1 internally knows how to handle that, right? So this is basically how B4 works in principle. Now you might see that there are some similarities between this setup and the setup that we learned in the last class, right? So in the last class, this flashing is basically demonstrating that these routers are physically close to each other, right? So this, this B4 transit is geographically distributed, and all these individual routers that are enabling the peering are at the same location, right? And then the routers that belong to the B4 are geographically distributed, and they're using the internal gateway protocol to communicate information with each other, right? So what I was telling you earlier is that there is a similarity between what we see here versus what we learned in the last class. So in the last class, what we learned was that SDX was providing flexible control of connectivity between these edge sites or different ASs, administrative domains, who were using BGP to communicate with each other, right? So the difference here is that SDX was local. In a sense, there was a co-location between the routers that belong to these sites and the other participants, right? So in this case, one site can be in LA, the other site can be in New York, right? So the design choice here is that either you provide a layer 2 connectivity between New York, like a router which is sitting in New York and the router which is sitting in LA, right? Which provide a layer 2 switching fabric to do that, or you use the layer 3, which is the routing protocol like IBGP protocol, right, to provide that internal connectivity. So I would say that it is technically possible to provide this layer 2 switching fabric and think of B4 as one big switch, right? But Google made a choice not to do that. And I am not saying that they didn't consider it or they considered it and denied it. We don't know, because B4 came out before SDX came out, right? So SDX came out in SIGCOMM 2014 and B4 came out in SIGCOMM 2013. So before that, nobody knew that this type of SDX set of ideas are even possible. So that might be one reason why they didn't even consider that design choice, right? But logically thinking, if the whole idea of software-defined networking has been that can you provide an abstraction of one big switch, express all the policies, all the flexible things that you want to do, and then use OpenFlow to enable that one big switch abstraction, right? And that's something that we learned in Pilotic as well. But there is a logical reasoning behind treating B4 as a transit provider and like providing layer 3 connectivity, is that there are a lot of mature tools and engineering expertise that lies around managing BGP set of routers, right? So I think that was kind of like a more of a engineering decision that they had to make, that which skill set, like how many engineers can we get for a particular skill set, right? So there are hundreds or maybe thousands of engineers who can be termed as experts of BGP, but maybe there are tens of maybe at best hundreds of engineers we can say expert of SDN. And to run an operational network of the scale, they have to make a choice, like where exactly the skill set is. So that might also be one factor that drives this decision about whether they want to use BGP or whether they want to use one big switch abstraction. But like as an intellectual exercise, I would argue that this one big switch abstraction is possible. And with the tools and techniques that we have right now, and especially the kind of pool of engineers that we have right now, I would argue that we can think about or rethink about B4, like implementing B4 as one big switch abstraction, right? So the similar ideas that we had for ISTX can be expanded in this context, and you can think about this B4 IXP type of thing that is providing connectivity between different sites, satisfying different traffic engineering goals. I think like one challenge that one has to face here is that when you're providing this big switch abstraction and the intermediate devices are actually like layer 3 routers, right? So the the software defined networking is only happening at the edge sites, right? So at an ingress, you have like let's talk about it here, that the router that we see here is the one that is at the same site as site 1, right? And then it is connecting to other routers. But in this figure, for simplicity, I'm showing all these routers that are connected to some sites, but there will be some intermediate routers as well that are carrying the traffic from site 1 to site 2, right? So those routers in this current setup, they don't need to change at all, right? So if you're supporting iBGP, they just need to run iBGP, and you can use Cisco, Juniper, whatever devices. So right now in this design, those are not software-defined routers, right? So the only software-defined part is this router, which is sitting at the edge at each of those sites, right? So that is a bit of a difference. So the approach that I'm suggesting here with one big switch abstraction, all the devices in the network have to be programmable devices, right? Or you have to like find some intelligent interfacing between these devices so that you can enable that, and you can do that at scale, right? So that's kind of like a trade-off apart from the engineering talent pool that I was arguing earlier as well. But intellectually, it's a very interesting exercise to explore. All right, so now let's dig a bit into the B4 architecture. Clusters are basically the set of servers that are all connecting to these bunch of open flow switches at each site. And then these sites are using eBGP to communicate. So the site A here that you see the green bubble is basically the router that you see here, right? So this is abstracted as just one router, but technically there are multiple switches that are enabling that functionality, right? And these are all open flow, like these are switches that are supporting open flow. So OFA here is referring to open flow agent, right? And then these routers have iBGP session with the site routers at other sites, right? So site A will have a iBGP session with site B, and so is the case for site C, right? And then they're having an eBGP session with the routers belonging to the data center cluster. Now, at the controller level, each of these sites are managed by site-specific controllers, right? So in those site-specific controller, you have NCS, which is a network controller system, and then at the top of it, you have a bunch of applications that are running. OFC is Open Flow Controller, right? And Open Flow Controller has a bunch of applications running. So one of them is called RAP, which is, I believe, routing application proxy something, and TE agent, which is for the traffic engineering. And then it is like, what is interesting and important is that it is using a software called Quagga. So I don't know if any of you are familiar with Quagga, but Quagga is, you can think of it as a Swiss knife of software routing, right? So Quagga basically implements all the routing, all possible routing protocols that you can think of in software, right? So as long as you provide the right abstraction between or like this software implementation, the hardware implementation, it works fine. And this is a software which SDX also used to emulate the BGP protocols for the participants at the SDX, right? So Quagga is a very, very handy tool, and I'm pointing it out because if you are planning to do any term project which is related to routing and implementing any type of routing protocol in software, you might want to get familiar with Quagga, which is actually not very tough thing to do. It basically implements all the standard protocols, BGP, OSPF, ISIS, and all those protocols. So it can be very handy, right? And then all of these site controllers are connected to a gateway, and this gateway is supposed to abstract away all the low-level details and provide a high-level abstraction to a centralized traffic engineering server, which is going to make decisions about the traffic engineering, about like what type of traffic should be going through which tunnels and all those. Like we will cover that. So this is overall the architecture of B4. And now let's think about how the BGP, which is the routing protocol, is integrated with OpenFlow in this case. So, like as I mentioned, the Quagga is the one which is running the BGP and ISIS protocol for eBGP and iBGP sessions. And then what it does is that, like BGP is supposed to receive the updates from its peers, right? So it receives an update which is, hey, I have routes to these prefixes. That is an update, right? Or for some reason, if certain links are down, then it might advertise that, route withdrawal messages. It will say that, okay, like, no, I don't have any route for the prefixes that I advertised earlier, right? So that there can be route advertisements and there can be route withdrawals, right? So like the Quagga's routing protocol is supposed to process all these messages, and based on all the messages that it has and some sort of route selection policy that you have programmed, it is going to compute a RIB or a routing information base, where it will say that, okay, for which set of prefixes, or for so it will have, think of it as a match action table, right? So on the match side, there will be destination IP prefixes, and then on the action side, you basically not really an action, but it's like the interface here, which is like what set of interfaces the traffic should be forwarded to, right? So I would say the action is forward and whatever interfaces that you see here, right? So in this case, when it says 1.2.3/24, so that is a prefix, and for that prefix, you can send traffic either to interface 0 or interface 1, right? And this is the routing information base that it will create for all the prefixes that it has seen, right? So these prefixes are the ones that are advertised by individual sites, right? And then using the remote procedure called RPC, these will be sent to the RIP cache for the RAP server, or basically the sites, the RAP server within the site controller. And then this will be translated into the flows, which are equivalent of the match action table entries that will be pushed down, and then ECMP groups that don't know what set of groups belong to the same category, so that you can do this load balancing across the two set of interfaces. And then it uses OpenFlow protocol to send this information down to the hardware switches. At the switch, you have an OpenFlow agent, and the OpenFlow controller is basically using ONIX, and it has this NIB abstraction, the network information base, right? So the RAP server is basically doing a translation between the RIBs and the NIBs and the NIBs and the RIBs, right? So these are two different levels of abstraction that are out there, and the RAP server, this RAP service itself, is providing that type of translation for us, right? So this is how these two protocols are integrated. We didn't cover this level of detail in SDX, but this type of translation does happen in SDX as well, right? So if you recall that in SDX, we were talking about the metadata getting added to the packet, right? So the metadata was getting added to the packet using a combination of BGP protocol and the ARP protocol, right? So it was first asking that, for this prefix, what is the next hop IP address? And using the BGP protocol, it gets an answer to that. And then for that next hop IP address, it was asking what is the MAC address using the ARP protocol. And then the SDX controller is manipulating both these control messages to make sure that this metadata is added to the packet as a destination MAC address, right? So these type of, like I would say trickeries did happen in SDX as well. But in the B4 setup, it has a completely different service altogether for it. One thing that will be interesting to know here is that for the Quagga, like the routing protocols running in Quagga, they need to know what advertisements are coming from the peers. So that advertisement will actually come in the data plane, right, at the switch. So from the switch, that information needs to be sent up to first the OpenFlow controller, from the OpenFlow controller to the Quagga service, right? So that that translation has to happen. That type of message handling needs to be enabled, and that's something which the B4 enabled as well. So let's quickly talk about traffic engineering here. So traffic engineering with B4 has 2 or 3 main components. One is that it has this gateway abstraction. The B4 has a gateway abstraction that it abstracts away all the OpenFlow specific details, right? So it basically looks at all these sites as individual nodes, and then it basically decides that how much traffic needs to come in, what type of applications are out there, and then what type of routing paths do exist, or how many tunnels do exist between each of those sites. And then it computes these decisions about, okay, what type of bandwidth enforcement should be applied at each of these sites. And then for the traffic that is supposed to go from one ingress to egress, how that has to be divided between different tunnels, right? So maybe I should talk about that in a bit more detail. So traffic engineering server operates over 3 or 4 pieces of information. One is the network topology graph, right? So this is the abstract graph that is provided by the SDN gateway. This represents sites as vertices and site-to-site connectivity as edges, right? And then you have a flow group where rather than looking at traffic or making decisions for one flow at a time, you group a bunch of flows that have the same set of requirements, right? So all applications that are tolerant to delay, they will be grouped into one, they will be clubbed into one group. The others, like delay sensitive, will be clubbed into others, and you make decisions at that level of granularity. That helps with the scalability of the problem. Then you have these tunnels, which are basically the site level paths. So different possible paths that you have between each of those sites, right? And then finally, it is computing the tunnel groups, which is mapping between the flows or the flow groups and the tunnels, right? So I'm not going to get into the details of this traffic engineering problem, but I would say that if you are interested in linear algebra, there are very nice formulations for these problems on in the SWAN paper. And it's an integer linear program optimization. It is NP hard, so there are some optimizations as well that they have proposed. But if you're interested, I would highly recommend you to read the SWAN paper. I have used that for a couple of projects that I've worked on. It's very elegant. And then there are a couple of follow-ups, which are if you add more complexities to the problem, there are more dynamism that's going on. Like, how do you handle that? So that's all interesting stuff. And I will highly recommend, if you want to get exposed to it, take a look at the SWAN paper. All right, so this is a time to conclude the talk. So what are the takeaways from this, right? So I want you to have a couple of takeaways here. One is that there are 2 types of WAN. All WANs are not the same. One that connects the backend to front ends, right? And the other that connects the backends to backend. So in this class, we focus more on the second category, and B4 is one example of that, right? So SWAN is the example for Microsoft. So there are a couple of examples of that. And in the next lecture, we will be focusing more on the other type of wide area network, which is the backend to front end B2 type, right? And we will talk about Espresso and Edge Fabric, which are the implementations for Facebook and Google, and see how these ideas have adapted and transgressed to the other type of wide area networks. Before SD-WANs were introduced, so the usage was MPLS was prevalent. And as we saw, that it can be very inefficient, and that can help, that can contribute to under provisioning, of these devices most of the time. Sorry, over provisioning, so that you're underutilized most of the time when you do over provisioning, and that is basically inefficiency that is not sustainable in the longer run. So something had to happen, and what happened was these software-defined WANs. B4 is one instantiation, and it is designed as a software-defined transit provider for the data center sites. And then it basically talks about how that transit provider functionalities can be made more flexible using the OpenFlow switches, such that you don't have to buy those expensive Cisco Juniper devices and get the functionality that you don't need, right? So this is the takeaway from this lecture. And in the next lecture, we will discuss about the other type of wide area networks. All right, thank you for your attention, and I'll be uploading the slides or this talk very soon over YouTube. All right, thank you.